All right, so we're pretty much just going to pick up with what we left off with last time, discussing combining in acids and bases together. But now we're going to do so in the context of a titration. All right. Who here has performed a titration in the lab before? Great, right? So that uses that tall column with those volume markings on there, what we call a burette. You fill your burette with some titrant. All right, that's what lives in your burette here. And then you're going to add slowly, drop by drop, into this flask. All right, and so for this example here, and probably what you did was you used a base as your titrant, most likely sodium hydroxide, and you had some acid in your flask, right? And what you saw is everything was all clear and colorless, but then you also add this indicator in there, this acid-base indicator. And what happens is when you added a drop or a few drops, all of a sudden that solution turned kind of pink, but then you swirled and it disappeared. And then finally you got to the end point of your titration, which is when it flipped to be all pink and you couldn't get rid of it, and then you stopped. Right? That was this acid-base titration. So in Chem 1A, your goal was what we call the equivalence point. And we're going to see this terminology come up again, discussions of this equivalence point. That's what you stopped at. When it turned pink, you stopped there because it reached the equivalence point of this titration. And importantly, at the equivalence point, that means that the amount of acid that you had in your flask initially is now equal to the amount of base that you added in there. And this was sort of your goal in Chem 1A, is you started out knowing how much acid you had, and then you use that to figure out what the concentration of base was, or vice versa. Usually we do both. So then we know what's in our titrant here, we know how much base we have, we do some stoichiometry, calculate how much acid we have. All right, so it was all about finding your equivalence point here. We're going to have a very different goal in Chem 1B. Okay, in Chem 1B, our discussion has been all about pH. And so our goal here when we're talking about titrations is to calculate the pH of that solution at each point in your titration. All right, so we're no longer just getting to the equivalence point and then using that data. Our goal is to figure out, after I add 1 drop of base, what happens to the pH? After I add 10 drops of base, what happens to the pH? We want to know what happens to the pH at every point along the way in this titration. Cool. All right, so we're going to start off with a strong acid, strong base titration. All right, if we did this, right, we did our titration and we calculated the pH at every point along this titration, we would get this curve that looks something like this. Okay, and so this is our goal, is we're going to pick a point in this titration and we should be able to calculate the pH of that solution. All right. Clearly, we're not going to do the 40 billion calculations that this computer did in order to get this pretty curve here. But nonetheless, we could just pick, our goal is to be able to calculate the pH at any point along this curve here. Okay? So first of all, we're starting out with strong acid in our flask, which is why our pH is very low at the very beginning of this titration. Right? My pH is on my y-axis here. My volume of base added is on the x-axis. So as we add base, we start increasing the pH of our solution. And then we get to this point here where it shoots up really high, right? Shoots up in this near vertical region. And now we're adding base. Our pH is still increasing, but much more slowly. Okay? So first of all, what we're going to do is, this is our goal, calculate pH at any point along the way of this titration. And what we're going to see is we're going to have a little bit of a different strategy for how we calculate pH, depending on where on this curve we are. Okay, so we're going to break this titration curve into these regions, and we're going to talk about how we calculate pH in each one of those regions. All right? So the first region is just this very first data point on that graph, which is when we only have a solution of strong acid and we haven't even begun our titration yet. We haven't even begun to add base. All right? So region 1 here is simply a solution of strong acid. Do we know how to calculate this, the pH of a solution of strong acid? All right, so that's exactly what we're going to do for this particular point in our titration. We'll calculate our pH of our strong acid solution. Okay, importantly, that uses that concentration of acid is simply equal to concentration of hydronium business, right? Because that reaction goes all the way to completion, that acid dissociation reaction. Cool, all right, so let's do it. Okay, again, we're going to call this region 1, solution of strong acid. Okay, a student prepares 50 ml of 2.5 molar HCl. Okay, what is the pH? All right, so given what we've discussed about our strong acids, everybody take a second, calculate the pH of this solution. All right, so this is quite a concentrated solution of this strong acid, 2.5 molar. Importantly, my HCl concentration that I have initially is just going to be equal to the amount of hydronium that's formed when all that HCl dissociates at equilibrium. So my hydronium ion concentration is that 2.5 molar. So in order to calculate the pH of this solution, I'm going to take the negative log of that concentration of that 2.5. All right, and we get negative 0.39794. All right, and yes, pHs can be negative. So if you have a very concentrated solution of acid, you will get a negative pH. That's not an illegal thing. pHs don't have to be between 1 and 14 or 0 and 14 or whatever it is. There's really no bound to what your pH can be. It can be higher than 14. It can be lower than 0. All right? That just means we have a very acidic solution here, one we really don't want to spill on ourselves. And then because this is this simple calculation here, right, I didn't have to use an ice table to get here. For these simple calculations for strong acids and strong bases, we have this expectation that we can carry our sig figs. So everybody, let's remember here, how many sig figs do I have in this 2.5? 2, and that's going to correspond to how many what in my answer? How many decimal places? All right, so my pH here, reported to the correct number of sig figs, is negative 0.40. So going back up to our curve here, how do we deal with the very first point on our curve? Well, that's just a solution of strong acid. We know how to calculate the pH of solutions of strong acids. All right? Now we're going to go ahead and start our titration. So I'm going to pick a point along this point of our curve here. Okay? And we're going to do an example problem first, and then we'll go back and label this region once we see what's going on here. All right, so here we have now our region 2. We're going to take this same solution, this 50 mils of 2.5 molar HCl. And now we're going to titrate in 25 mLs of 2.1 molar NaOH. And we want to know, what is the pH? All right, well, what's going to happen when those hydroxide ions come into contact with those HCl molecules? What are they going to do? They're going to react to form water and some other conjugate, some salt. All right, so we need our acid-base reaction. All right, we need to figure out what reaction is happening between HCl and NaOH. Given what we discussed last class period, I want everybody to take a second and write that balanced chemical equation for the reaction between HCl and NaOH. Okay, so first of all, in our sodium hydroxide, what's the sodium doing for us? Nothing, right? So those counter ions, you can include it if you want, and I'll show you where you would have to put it if you did decide to include it. But I strongly recommend you get in the habit of just erasing it and putting a minus sign in there. The hydroxide ion is really what's playing the role. I say that because that's a nice skill to have when you go to organic chemistry. You're going to see that a lot as well. All these ions where the sodium's not doing anything, and it's the other thing that's really important. Okay, so I'm going to take my acid formula, I'm going to decrease my number of hydrogens and decrease my charge. So that's the chloride ion. Importantly, if you did want to include your sodium in this equation, that's where you'd have it, is paired up with that positively charged sodium ion paired with that negatively charged chloride ion. All right, I'm going to omit it because, again, that's how I like to look at it. And then for our conjugate base, our conjugate acid, we're going to take our base and we're going to add a hydrogen and add one to its charge, giving us water. Okay? So we have our acid-base reaction, and we need to keep track of how much of this reaction has occurred. How do we do that? What's our strategy that we've been using? The ice table. All right, and here's going to be the big difference, the big pain in the butt difference of this discussion of titrations than what we were just doing last class period. All right, we're going to make an ice table here. And previously, when we made our ice table, our units that we were using were molar, right? The concentration. Practically speaking, that's not really the best way to do it. And titrations kind of prove why this is problematic here. All right, we're going to combine a certain volume of our HCl, and we're adding a set volume of this base to it. And since we're changing our volume, that's going to change our concentration. Even if I added just water to this hydrochloric acid solution, by changing the volume, I would change its concentration. It would no longer be 2.5 molar once I added in this new volume here. All right, so we're not going to be allowed to do our ICE table in units of concentration. What isn't going to change is the number of moles of hydrochloric acid and the number of moles of hydroxide that are there. And so what we're going to have to do is incorporate what we learned about solutions and concentrations into our discussion of reactions. Our ICE table here has to be in units of moles. All right, and really the trick that I'm going to show you, and not always, but in this case and often because we like to work in small quantities in chemistry. We're not trying to do titrations with like 20 liters. It'd be possible, but it would be very expensive, and there's no real point to doing it that much, right? So we use smaller volumes like milliliters, which means that it's going to be more convenient to bookkeep in units of millimoles. All right, you can always just convert to moles if you hate this idea of millimoles, but I'm going to show you how to do it in millimoles because it's going to save us a step. Okay, so first of all, I'm going to bookkeep each one of these components here. So now I'm going to make an ICE table here, but I'm going to be talking about HCl millimoles, hydroxide millimoles, chloride millimoles, and water millimoles. And we're still going to have those three rows. For our ICE. Okay. So I have this specific volume of our HCl here, this 50 mils, and it's got a concentration of 2.5 molar. So I'm going to take my 50 mLs. I'm going to multiply it by that concentration of 2.5 molar, but I'm going to split up my units, right? So it's going to be 2.5 moles of HCl over 1 liter of solution. Okay? Now, if we really hate this, we can always stick another conversion factor in here that's going to jump us from milliliters to liters, and then we'd be in units of moles. Okay? But then we're going to get this really tiny number. It's going to be kind of a pain to work with. So we're going to leave things in units of millimoles, and that's just going to allow us to skip this step right here. If we notice, my liters will still cancel out. What I'm left with are milli and moles. All right, so our units here are going to be in units of millimoles. Right? So really I have 125 millimoles of HCl in this reaction. And importantly, that number is not going, the number of moles won't change. You know, maybe it'll be consumed or something like that. But unlike concentration, we're going to talk in terms of millimoles. All right, so everybody's going to take a second. How many millimoles of hydroxide do we have? We said we had 25 mils of 2.1 molar. right, so I'm going to take that volume multiplied by my concentration, moles over liters. The liters part cancel out, and I'm again left with the milli and moles. All right, and before any reaction has occurred, I don't have any product. Okay? So I'm going to do my change box, that variable x. Reactants decrease in concentration, so I have a negative sign. Products increase in concentration, so I have a positive sign. And then to get my E box, I just sum up those first two rows. 125 minus x, 52.5 minus x, x, and x. All right, we talked about combining acids and bases last class period, and that this reaction here is going to go 100% to completion here. All the strong will react, right? But I'm going to be limited by the amount of one of these two reactants. I have a limiting reactant in there that's going to be consumed first. Based on my ice table here, what is my limiting reactant in this particular problem? A hydroxide. I have less hydroxide than I do HCl. All right, so my hydroxide is limiting. We would call our HCl is in excess. And this is the real defining feature of region 2 on our curve here. In region 2, we still are at a very low pH because yes, we've added some base, but in this region, we still have an excess of that strong acid, all right? So we're gonna say region 2, we have an excess of our strong acid / a limiting amount of strong base. Okay, so then how are we going to calculate the pH of this solution? Well, let's just finish this off here. We need to use our ice table to figure out how much of this reaction has occurred. Everybody take a second, see if you can't fill out a solve row here. All right, how much of this reaction has occurred? What are we left with at the end? All right, well, since this reaction goes 100% to completion and my hydroxide is limiting, that means all of that hydroxide is going to get consumed, meaning my value of x must be 52.5. So plug this in across the way here, we get 72.5 millimoles of our HCl remain. And then we've created 52.5 millimoles of chloride and 52.5 millimoles of water. All right, so again, this reaction goes all the way to completion here. So all of my limiting reactant is going to be consumed, leaving me with nothing. That allows me to solve for my value of x and plug it in everywhere else to figure out how much I have remaining in solution. Okay, now we're talking about the pH of this solution. So yes, I created 52.5 millimoles of chloride, but do I care? No, and why don't we care about the chloride? Yeah, it is blue. No, chloride's fine. No, because yes, it is neutral. And water also created, but not going to influence the pH of our solution. Neutral. So the only thing that I care about that I'm left with here is my excess strong acid. So how do we calculate the pH of this solution? It's a strong acid, right? So the concentration of strong acid is going to be equal to that hydronium concentration. Okay, so now we're going to calculate our pH. All right, we know that pH equals the negative log of the concentration of hydronium. But we sort of have a problem here. Because when I did my ice table here, is it in units of concentration? No, it's in units of millimoles now. So now I got to put it back in units of concentration here. So first, before we can even calculate our concentration, or calculate our pH, step one, we got to calculate our hydronium concentration. All right, so bracket means concentration in molarity, which is what over what? Moles over liters. But I'm in units of millimoles. All right, well, I can, if I'm in units of millimoles and I'm trying to get to concentration, I need to cancel out that milli. So I can just take my millimoles divided by milliliters. Now all of a sudden that milli part cancels out and leaves me with moles over liters or molarity. All right, so hydronium concentration. We're going to calculate that by taking our millimoles divided by milliliters. That will give us the molarity of that solution. We said we had 72.5 millimoles. How many milliliters do I have? Let's look carefully at our problem here. We took this 50 milliliter solution, and when I titrated in 25 mils, what does that mean? It means I added it to it, right? So now my solution volume is no longer 50 mils. My volume's changed. That's why we had to put it in millimoles to begin with, right? Because we're adding volume. So yes, I'm going to have to figure out my new volume by adding those two together, or I'm in 75 mils of solution here. All right, and that equals 0.9666666 repeating forever. All right, and again, the milli canceled out, leaving me with units of moles per liter or molarity. So now I can calculate my pH. Negative log of the hydronium ion concentration, plugging that into my calculator. I get a pH of, we're just going to put 3. Now that we did our ice table, we get to kind of quietly abandon sig figs here. So let's just put 3 decimal places down. 0, 1, 5. Okay? Comparing to our original pH of that very acidic negative 0.4, my pH has increased a little bit, but I have an excess of strong acid in this solution, right? Even after the acid-base reaction occurs, I have an excess of HCl, so we still are at a very low pH here. Okay? So in terms of our strategy for excess strong acid limiting strong base for region 2, we have to calculate the amount of acid-base reaction. All right, using our ice table. Our ice table, again, we got to do it in millimoles for titration since we're changing our volume. Once we figure out how much we have, what's happened after that reaction has occurred, because we have an excess of strong acid, all we simply have is a strong acid solution. And we know how to calculate the pH of a strong acid solution. We're also just going to remind ourselves that we have to convert back to big M molarity. All right, so this whole bit here would be considered region 2. I guess without that start. So starting here, boom. Our third region is again just one point on this graph. This point right here. This is the midpoint of that vertical region, and this is what's called the equivalence point. Our equivalence point, as we said at the beginning here, this is where you stopped in general chemistry. That's when the amount of, in this case, HCl that we have, let's just say, amount of acid that we have initially is equal to the concentration of base that's been added. Okay? So, I'm going to do this the long way, just to prove a point here. All right, see, I wouldn't bother trying to copy all this down here, because I'm going to show you that there's no point in doing it the long way. All right, so we're region 3 at our equivalence point here. We have the same acid-base reaction. Okay, we're going to start out with our same solution of HCl. So we still are starting out with those 1.25 millimoles of HCl. Okay. Importantly, in terms of strategy-wise for our calculation, and the previous step, we determined that we had reacted some of that. So now we only have 72.5, right? You could pick up with that number and like keep on doing your calculation, but it makes it so much more difficult. Just go back to that original solution, its original solution concentration, and then work with there, pretending every single time you did your calculation, rather than picking up with where you left off last time. You're starting over brand new again and just adding a certain amount of that titrant to it, right? So my strategy here is going to be not to pick up with that 72.5 number, but I'm going to go back to that initial amount that I had at the very beginning of the problem, all right? It's equivalent from a calculation standpoint, except for way less steps, way fewer steps. Okay, if I'm at the equivalence point, how much base would I have added in there? The exact same amount, right? That's what it means to be at the equivalence point. So 125 millimoles, all right, because we're at the equivalence point. So if I have the exact same amount of acid and the exact same amount of base, are either one of these limiting? No, I'm at that perfect point where I have the exact number of moles of each of them. So if we fill this all the way out here, we do our change box, and again, you don't have to do it the long way. I'm going to prove a point. 125 minus x. Well, neither of these are limiting, or rather, I guess they both are in the sense that they're both going to be consumed all the way, meaning my value of x is 125. So at this point in my titration, I have 0 strong acid left over, 0 strong base left over. All I've made is a solution of chloride and water. All right. However, what do we know about this, the pH of a solution that's just chloride and water? What are the two of those in terms of our pH? Are they weak acids, weak bases, or neutral? They're neutral, right? This one's neutral. This one's neutral. Which means at the equivalence point of a strong acid, strong base titration, what must my pH be? 7. So if we look here, strong acid, strong base titration, since my conjugate base and my conjugate acid are by definition neutral, the pH of that solution would just be neutral. All right? So this is kind of best case scenario. If I ask you for the pH at the equivalence point, it is always 7. For a strong acid, strong base titration. All right. Okay, but what I could ask you, another thing that I could ask you though, okay, and this is going to be the real sort of region 3 calculation here. Again, let's take our original solution. All right, but now I want to ask how much 2.1 molar NaOH is added to reach the equivalence point. Now, since this is a titration and we're going to be changing our volume, again, we want to kind of redefine our equivalence point. Yes, it's the concentration of acid initially is equal to the concentration of base added, but it's also millimoles of acid that we have initially are now equal to the millimoles of base added. All right, how many millimoles of acid did I start out with initially? According to our ice table calculations, we took our 50 milliliters, multiplied it by that 2.5 molar solution. That gave us 125 millimoles of acid. Okay, so I want everybody to take a few minutes here. See if you can't then calculate how much of this 2.1 molar NaOH solution I would have had to have added in order to reach my equivalence point, to react all that 125 millimoles of acid perfectly. so if I know that I initially have 125 millimoles of hydrochloric acid, that means that at my equivalence point, I must have added 125 millimoles of sodium hydroxide, right? That's what it means to be at the equivalence point. So if I'm talking about how much, what volume I needed to add, I'm going to have to incorporate my concentration here. Remember we talked about how that 2.1 big M, if we're going to use it in our math, we should put it 2.1 moles over 1 liter. All right, and since I know how many moles or millimoles of this NaOH I've used, or added rather, I'm going to use my conversion factor here, but I need to cancel out those units of moles, so I'm going to divide by that concentration. All right, so let's punch this into our calculator, 59.5. What are my units here? Does anything cancel out? What cancels out? The moles. All right, let's get rid of the moles. So what are we left with? Milli and liters. So 59.5 milliliters will be my volume added. And that's how much of that base I had to add in order to get to that equivalence point. All right, now in your titration, that's where you stopped. You stopped at the equivalence point and you did a bunch of stoichiometry. But again, that's not our goal here. Our goal is to figure out this pH at every point along the way here. So we're going to go past our equivalence point to now our last region on this curve, region 4. And if I had an excess of strong acid down here, and then I reached this point where they were exactly equal, and I kept on adding more and more base, what do I have an excess of up here? That's strong base, right? Which is why we're at a nice high pH for this region. Okay? So our last region here, and we'll do an example calculation. Let me make some room. Our region 4. This is now where we have an excess of strong base. And that's limiting amount of strong acid. Okay, so we're going to do our region 4 calculation here. Since I'm in region 4, I got to be past my equivalence points. So now we're going to add 75 mils of that 2.1 molar NaOH. And I want everybody to take a second. Given the same strategy that we've been applying, we have our acid-base reaction. We need to keep track of how much reaction has occurred using an ice table. And again, we have to be in units of millimole for these pH problems. All right, so given what we've discussed both today and last class period, take a second and see if you can't calculate the pH of this solution. Again, we need to convert to millimoles, so we're going to take our initial times that concentration in moles per liter. That's how we got that 125 millimoles. Now we got to do the same thing for hydroxide. Now we're saying we've added 75 mils of that 2.1 molar solution. Sorry, give me a second. I realized this other slide wasn't prepared, so quietly do that while you're working. All right, as we said, at this point, we reached our equivalence point where they were equal, and then we kept on adding more and more base. That means that now my hydrochloric acid is limiting, and I have excess strong base. So what's that value of X going to be? When I solve my ICE table here, what will X be? 125, right? Because this is my limiting reactant gets consumed. That means X is 125, so I can go across, fill these all in. And importantly, my 157.5 minus 125 leaves me with 32.5 millimoles of hydroxide. And now we get to our pH calculation, our calculate pH portion. All right, but just like before, because titrations are a pain in the butt and we had to convert to millimole, that means before we can do any pH calculations, we're going to have to calculate, in this case now not hydronium, but hydroxide concentration. Using that definition of concentration of moles over liters. Or for our sake, because it's going to be more convenient, we want to use millimoles over milliliters. ice table tells me I have 32.5 millimoles of hydroxide at equilibrium. And what's the volume of this solution? Is it 50? Is it 75? No, it's the two of them together, right? I've combined those volumes. Now we got a total of 125 mils. Meaning that our concentration of hydroxide is 0.26 molar. Now we can do our pH calculation. Okay, we take the negative log of 0.26, and our calculator spits out 0.58 something something, say 585, and we're done. No, because that 0.26 was not hydronium concentration, but hydroxide. So what did we really just calculate here? POH, which is fine. That gets us part of the way there. We just don't want to forget and stop there. Okay? We need to now use the fact that our pH plus our POH equals 14, or pH equals 14 minus POH. And this gives me a nice number that makes sense for being in this excess of strong base region of 13.415. Right, so in region 4, now we have an excess of our strong base. Our hydrochloric acid is limited, which means after our acid-base reaction occurs, we're going to be left over with a solution of strong base. And then we just calculate the pH using that solution of strong base approach that we learned. All right, so let's just finish off our notes up here about how we were calculating. So first, again, we're going to calculate amount of acid-base reaction. And then what we're left with is just a strong base solution. Again, maybe we should put a note that we're going to need to convert back to molarity in order to do it. Okay, so this is our strong acid, strong base titration here. We're starting out with a flask of strong acid, and we're titrating in some strong base. So when we're starting out with a flask of strong acid, we're starting at a very low pH here, and our strategy for calculating pH in this region is to just simply calculate the pH of a strong acid solution, right? Using the concentration of acid is equal to the concentration of hydronium for a strong acid. Now we get to this region here, region 2, where we've started our titration, but we haven't quite reached our equivalence point yet. That means we have an excess of strong acid and a limiting amount of strong base. So we got to figure out how much reaction has occurred. All right, so we're going to calculate the amount of acid-base reaction. Maybe we should just we do that in moles or millimoles. And then after we convert back to molarity, since we're left with just a solution of strong acid, we use our strong acid solution approach. All right, then we get to the equivalence point where we have exactly the same amount of acid and base molecules in that solution. And since this is a strong acid and a strong base, their conjugates are both neutral, meaning that our pH is always going to be 7 at the equivalence point for a strong titration. And then we get to that fourth region where now we're past the equivalence point and we've kept on adding more base. So we have an excess of strong base and a limiting amount of that strong acid. We again need to calculate how much reaction occurred, and we're going to do so again in millimoles. And And then after converting back to molarity, we can calculate the pH of that strong base solution. Cool. All right. Now we're going to go on and we're going to talk about a weak acid strong base titration. So I'm going to take some weak acid, I'm going to titrate in my strong base hydroxide. I'll get my conjugate base and my conjugate acid of water here. Okay. And again, we're going to break this into these titration regions. So again, we're going to see we have a little bit of a different strategy depending on where we are on our titration curve. I'm going to show you an example of a titration curve for a weak acid strong base titration. And you see it looks pretty similar, right? We got that same S-curve shape going on. Okay. We start out at a low pH. It's not quite as low because we're talking about a weak acid now. And then it again has that vertical region before flattening out at some very high pH. So we see that same kind of basic structure. Okay? And our regions are going to be very much so to cut this up in the same sort of way, where that very first region there is really just the first data point on that curve, my solution of weak acid before I've added any strong base at all. All right, so first region here, we have a solution of weak acid, meaning we're going to need to do a weak acid pH calculation, which are not as easy as our strong acid pH calculations. Remember, our weak acids are when we have to treat it out like an equilibrium problem. Okay, so let's do an example from region 1 here. Okay, now a student's going to prepare 70 mLs of a 1.25 molar solution of our acid here, C2. Acetic acid. All right, what is the pH? Okay, well, again, weak acids are a pain in the butt. So now I need a lot more information in order to calculate the pH of my weak acid here. We're going to need our acid dissociation equation. Once we get our acid dissociation equation, we're going to need that Ka expression. And then finally, we're going to have to use an ice table to find our equilibrium values and plug them in. All right, this is the exact strategy that we learned how to do for calculating solutions of weak acids, because I haven't started my titration yet. Okay? There is one other piece of information that y'all are going to need before I can send you off to do this calculation. What is that piece of information? The Ka value, right? We got to go to our constants page and find acetic acid's Ka value. 1.8 times 10 to the negative 5 is that Ka value for acetic acid. just kind of make note of it up here. All right, so this is something that we should know how to do for sure. This is what we did last week. You've already had homework on it and everything. I'm going to give you a few minutes to get a head start here, and then I'll go and quietly fill in work, and you can look up if you're having trouble. All right, one thing I want to throw out there here. Have we started our titration yet in this problem? Have we changed our volume of our solution at all? No. So we can use our ICE table back just like how we learned how to do when we were calculating weak acid solutions in units of concentration. All right, we don't have to convert. You can always convert to millimole if you want, but you're just going to add an extra step in the process. All right, we can use units of concentration since we haven't actually changed our volume yet. so filling out my ice table here, my initial concentration of my acid is 1.25 molar. I don't have any of my products from my acid dissociation equation. I guess just to start at the jump here, by acid dissociation equation, remember that is always that very special equation where we're reacting our acid with water to form its conjugate base and hydronium, right? These are the reactions that we have those Ka values for. And so now I got to treat it like an equilibrium problem to figure out what my concentration of hydronium is going to be at equilibrium. So that's why I'm doing my ice table here. All right, our reactant gets consumed, our products get produced. So 1.25 minus X, X, and X. Now, to be clear, because this is a very subtle difference about how we were doing this just a second ago when we were talking about our acid-base reaction, this is not an all strong reacts kind of thing, right? This is an equilibrium problem here. I'm not able to assume that this reaction goes all the way to completion, so I'm not going to assume that this is just zero down at the bottom here. In fact, there's not very much reaction that occurs at all, right? So I definitely don't want to assume all 1.25 molar of this weak base reacts. Only a little bit of it is going to react, all right? So that's why I'm not solving for X here by setting this box to zero like we were doing before, because this reaction does not go all the way to completion like the ones that we were doing before did, because those involved strong acids or strong bases, okay? So I gotta do this equilibrium problem here where I plug this back into my equation here, plug this into my equation here, this into my equation here, set that all equal to my value of Ka that I looked up from my constants page, that 1.8 times 10 to the negative 5, and solve for X, right? That's the name of the game here. All right, so at this step, we're going to plug in and solve. We get that 1.8 times 10 to the negative 5 equals X squared over 1.25 minus X. We had two different ways to do it. One was using our fancy calculator to get the real value of X using that solve feature. The other one, which I'm going to use here, was that small x approximation. All right, where I say, all right, well, since X is going to be such a teeny tiny number, 1.25 minus X is going to be basically 1.25. So I get rid of it from my denominator, and this just simplifies my algebra a lot. Right, now I just have to rearrange and solve. X is equal to the square root of that Ka value times that initial concentration, or 0.004, 0.0047, something. We'll leave it at that. So that's my value of X. And importantly, according to my ice table, X is the concentration of hydronium at equilibrium. So when I solve for X, I have my concentration of hydronium. I'm going to calculate my pH by taking the negative log of that hydronium ion concentration, negative log of that value of X, and I get a pH equal to 2.32. We'll do 3 decimal places. 2.324. Okay, and we'll pick up with this next time, but just to be clear, right, we're talking about titrations. We really only covered this first region of our titration curve, which is before we even added any strong base in there. So all we have is a solution of weak acid, and we learned how to calculate the pH of our solutions of weak acids last week. All right, we'll finish off the rest of this curve next class period.